Mohawk and welcomes cat and dimensions. Real-world problems involving quantities such as ages and dimensions. In this lecture, we will see how to use linear equations to solve problems involving time, distance, and speed. Most of us are familiar with the concept of speed. We know that when we travel faster, we get to where we are going in less time. Or we travel a larger distance in the same amount of time. Automobiles come equipped with speed measuring devices called speedometers, which indicate speed in miles or kilometers per hour. The indicated speed tells us how many miles or kilometers we would travel in a single hour, assuming we traveled at a constant speed for the entire hour. Let's say that we are traveling at a constant speed of 50 kilometers per hour. We can visually represent this motion by graphing our distance from the starting point versus the elapsed time. If we graph time on the horizontal axis and distance on the vertical axis, we see that our distance increases at a constant rate. Distance is a linear function of time as long as our speed is constant. Our speed determines the slope of the graph. The greater the speed, the greater the slope. Just as slope is defined as the change in the vertical coordinate over the change in the horizontal coordinate. If we travel 100 kilometers in 2 by multiplying this formula of St. Louis, traveling east at 60 kilometers per hour. How long will it take us to travel 290 kilometers east of St. Louis? We know from our formula that speed times which the variable travelers, speed of the train is 60 kilometers per hour. Since we are solving this equation for t, we want to rearrange the equation sides of the equation, cancel the fact that the train trip is 6½ hours. Now let's try a problem which involves two vehicles moving at different speeds. A car and a bus are each traveling at constant speeds in opposite directions on a highway. 3 hours after they pass each other, they are 360 miles apart. If the car is traveling 10 miles per hour faster than the bus, how fast is each vehicle traveling? If we let the variable s represent the speed of the bus, we can represent the speed of the car as s plus 10, since the car's speed is 10 miles per hour faster than the bus. We know that the time that each vehicle has traveled since they passed each other is 3 hours. Knowing that speed times time equals distance, we can now write the distance traveled for each vehicle. In 3 hours, the bus has traveled 3s miles. And the car has traveled 3 times s plus 10 miles. The sum of these distances must equal the distance between the two vehicles, or 360 miles. We now have an equation which can be solved for the unknown variable s. We start by using the distributive property to distribute the 3 to the two terms inside the parentheses. 3 times 10 the variable 30. Completing the arithmetic on the right, we subtract 30 from 360 sides beta of equals 55. Since s represents the speed of the bus's speed is 55 miles per hour. And the speed of the car is 55 plus 10, or 65 miles per hour. Having found the speeds for the two vehicles, we can check these results by multiplying the travel time times speed for each vehicle to calculate the distance traveled, and then confirming that the sum of the distances is 360 miles. The distance traveled by the bus is 3 times 55, or 165 miles. And the distance traveled by the car is 3 times 65, or 195 miles. Since the sum of these two distances is indeed equal to 360 miles, we know that our calculations were correct. For our last example, let's solve a problem involving a vehicle traveling at different speeds at different times during the same trip. Mr. Squidgiopoulos has developed a car which can transform into a high-speed flying machine. He decides to take his new vehicle on a test drive from Orlando to San Francisco. He starts by driving on the highway, maintaining a constant speed of 70 miles per hour. After some time, he switches into flight mode. Quickly reaching a cruising speed of just over Mach 1, 770 miles per hour. Upon reaching San Francisco, 2,450 miles from his starting point, he checks his watch and sees that it has been 5 hours since he started. However, he forgot to record the time that he switched into flight mode, so he does not know how long he was driving at 70 miles per hour and how long he was flying at 770 miles per hour. Fortunately, using algebra, it is possible to calculate how long he has traveled at each speed. Let's let t represent the amount of time traveling at 70 miles per hour. Since the total travel time was 5 hours, the amount of time traveling at 770 miles per hour is 5 minus t. Since distance is equal to speed times time, the distance traveled during the first leg of the trip is 70 times t miles. Likewise, the distance traveled during the second leg is 770 times 5 minus t miles. The sum of these two distances must equal the total distance traveled, or 2,450 miles. We now have an equation which can be solved for the unknown variable t. We start by using the distributive property to distribute 770 to the two terms inside the parentheses. Times finding the 270t is negative 700. The sides of the negative 3,800 by both div 700 by 2. Since t represents the amount of time traveling at 70 miles per hour, we know that the first leg of the trip took 2 hours. Likewise, the second leg took 5 minus 2, or 3 hours. Having found the times for the two legs, we can check these results by multiplying 50 and the times. Since the sum of these distance examples illustrate how to create linear equations to solve problems involving constant speeds. In each example, we use the relationship between speed, time, and distance which we saw at the beginning of the lecture. The first example involved a single vehicle moving at a constant speed. The total time traveled was unknown, so we represented that value as travel, producing an equation containing a single variable t. The equation speeds. Since area wrote of the speed constant periods were known, but the length of time for each period was not known. Each period as speed, distance. Expressions for time.